functions and graphs. Very, very long. Don't panic, we're going to break it up into different parts. Firstly, let's take a look at linear graphs. We all know y equals mx plus c. Straight line graph, there's the gradient measure of steepness, the y-intercept where it cuts through the y-axis, x-intercepts where the straight line cuts through the x-intercept. X-axis rather. Here we have a set of parallel lines. They have exactly the same gradient, but obviously they're cutting through the x-axis and y-axis at different places. Let's go straight into doing some sketching. So we've got it in the format y equals mx plus c, gradient is 3, y-intercept is -1. Whenever we're creating a straight line graph, we just need 2 points and we can rule through it. Typically, we could look for the x-intercept and the y-intercept. For the x-intercept, make y equaling 0 because along the x-axis, the value of y is 0. So we're just going to make y equal to 0 and solve for x. So make the left-hand side equal to 0, solve for x, I get 1/3, so I have the point 1/3, 0. And that's shown here. The y-intercept, so along the y-axis, the value of x is always going to be 0, so I substitute 0 into the rule to establish that y is -1, creating the point 0, -1, and there's that, and then I just rule through. Notice the format of this equation is not y equals mx plus c, but we can still find the x-intercept and the y-intercept and then rule. So again, the x-intercept, make y equal to 0. Solve for x, I get 3 on 2. So I have 3 on 2, 0. That's shown there, 1.5. For my y-intercept, I sub x equaling 0 to establish 3, 0. And of course, that shouldn't be 3, 0. It should be 0, 3. The x value gets listed first. Here's the point, 0, 3, and then we rule through. Another equation, x-intercept is y equaling 0. And if we do that, we establish that x is also 0. So we know that the x-intercept and the y-intercept is that same point. It's at the origin, 0, 0. So to rule up a straight line for this equation, we need 2 points. We need to have another point. And what we can do there is choose any other value of x and sub it in to establish a second point. So in this case, what's been chosen is x equaling 6. Here's my equation. I sub in x equaling 6 and establish that y is equal to 24 on 3, which of course is 8. So I now have a second point, which is 6, 8. So my Cartesian plane, I've got 6, I've got 8, I've got my second point, I place it there, and then rule through. There's the graph. So looking at quadratics now, we've got the rule y equals x squared. We can generate a table of values. So in this case, I've made x vary between -3 and +3. I've subbed those x values into this rule to produce the corresponding y values. I can now take the table of values and plot them as points on the Cartesian plane. And as you can see, we end up with the shape of a basic parabola. So that's the basic parabola. Let's look at some changes around that basic parabola. Firstly, let's look at dilations. So in blue, we've got the standard y equals x squared. In red, I've got y equals 3x squared. If I consider the point 1, 1, which is on the standard y equals x squared, then the transformation that's applied to create this red graph is that every y value has been multiplied by 3. So the point 1, 1 will become the point 1, 3. And that happens for all the values that are on that blue standard y equals x squared. In a similar way, I have the position 1, 1 on the standard graph. The transformation that takes place to become the green graph, y equals a half x squared, is that every y value has been multiplied by a half. So the point 1, 1 now becomes 1, a half. And what you can see here is that if a, the value in front of the x squared, is greater than 1, then the appearance of that graph in comparison to the standard will be that it appears more narrower. Whilst if it's a fraction in front of the x squared, then the appearance will be that it's flatter or shallower. Another transformation that we deal with is horizontal translations. Again, the standard y equals x squared in blue. If I have x plus 1 all squared, the effect is that the entire graph is picked up and moved horizontally 1 unit to the left. The easiest way of working out if it's going left or right is to take what's inside the brackets, make it equal to 0 and solve for x. So x plus 1 equals 0, x will equal -1. That means that we are taking the original graph and shifting it 1 unit in the negative direction. Same thing happens here. X minus 2 all squared. I'll take the x minus 2, make it equal to 0, solve for x to get x equals +2. That will indicate that I take the original graph and move it 2 units in the positive direction. So that's dealing with horizontal translations. I also have vertical translations. So you can see my original graph, y equals x squared. If I now consider y equals x squared take 4, then I have my original graph and I'm moving it down 4 units. So what's happening there is that every y value that we'll have on the original graph, I subtract 4 from it, which means I get the graph here in black. In a similar way, if I consider y equals x squared plus 1, that's taking the original blue graph, adding 1 to every y value. So in essence, what I'm doing is taking that blue graph and shifting it up 1 unit. I also have reflections, and I'll just consider the reflections in the x-axis. So I've got a negative in front of this x squared, so the effect of this is that every y value on this original blue graph has been multiplied by -1, meaning that the entire shape has been reflected in the x-axis to get what we have here in red. So as an example, the position 1, 1 will now become 1, -1. The position 3, 9 will now become 3, -9. Here's a summary of the transformations that are possible for the x squares. Let's take a look at the effect of the a. Alright, so that's the value in front of the x squared. If we just look at the magnitude, so that is that we ignore the sign, so it could be -3x squared. Let's just ignore the negative part and just consider the 3. So that's when we talk about magnitude. That's what those straight lines mean. If the magnitude, the size of that number, is greater than 1, then the graph will appear narrower. If the size of a is a fraction, that is it's between 0 but less than 1, then it will appear wider. If a itself, so including the sign now, if that's a positive number, then the graph will be upright, and therefore the turning point will be a minimum turning point. If a is less than 0, so it's got a negative, then the parabola will be inverted, and the turning point will be a maximum. Horizontal shifts. As I said to you before, the easiest way of working out whether it's moving left or right in comparison to the standard y equals x squared is just to take what's inside the brackets, make it equal to 0 and solve for x. So if we end up with a positive, that represents that we're moving in the positive direction along the x-axis. If it's negative, then it moves in the negative direction. The effect of the k simply shifts it up and down, and it's pretty clear to read. So if k is greater than 0, then we're moving in the positive direction along the y-axis by k units. If it's less than 0, we're moving down by k units. Of course, quadratic equations can also be in turning point form. The turning point always occurs at hk. So take what's inside the brackets here, solve for x, and that'll be the x value for the turning point, and then the k will be the y value of the turning point. The effect of a, the number outside the bracket, is the same as it was previously stated. So the magnitude of a, so if a is greater than 1, narrower. If the magnitude of a is a fraction, it will appear wider. If a is greater than 0, it will be upright. If a is less than 0, it will be inverted. Finding x-intercepts, just make y equal to 0 and solve for x. To find y-intercepts, then sub x equaling 0 into the equation and solve for y. If you get given an equation that is in expanded form, then you can apply the completing the square method to convert it into turning point form. Let's look at some examples. Here we have an equation. Firstly, write down the coordinates of the turning point. So x plus 1, make that equal to 0, solve for x, I get x equaling negative 1. So the x value is negative 1. The y value is 6. B, state whether the graph is a maximum or a minimum turning point. The value that we have in front of the brackets is negative 2, it's negative. So therefore, this graph will be an inverted parabola. Okay, so it'll be inverted. And that will mean that we'll have the turning point being a maximum value. So you can imagine that shape. So at the very top, you're going to have that maximum. C, state whether the graph is wider or narrower or the same as the y equals x squared. A is negative 2, that's a value in front. The magnitude is 2, that's greater than 1, so therefore it's going to appear narrower. D, find the x-intercepts. So for my x-intercepts, find my y-intercept, I apologize for that. Here's the standard rule. I make x equals 0, I solve for y to get y equaling 4, so 0, 4 is the y-intercept. Notice that to correctly answer it, I can't have y equaling 4, I've got 0, 4. That's a point on the Cartesian plane. That's what we're looking for. E, x-intercepts, I just make y equaling 0, and so 0 is there. I'd subtract 6 from both sides. I divide both sides by negative 2. I take the square root of both sides, which generates positive and negative square root of 3. And then finally I subtract 3 from both sides. So I have positive square root of 3 take 1, or I have the negative square root of 3 take 1 for the x values. Now that's how I should answer it, like that. That's what you show on your graph. All right, you give values as exact form in methods. But just to give you a feel for where that would be placed, you can put into your calculator to generate these approximates. Sketching it, there's my x-intercepts, note in exact format, y-intercept exact format, turning point exact format. So for each of these, A, B, and C, I need to provide the turning point, the dilation factor, and the y-intercept. So for A, turning point, 1, 4. The dilation factor is 3. I just take the size of the number in front of the bracket, ignoring the sign. Y-intercept, I sub x equaling 0 into it, and I produce 0,7. I also need to state whether it's upright or inverted. So because it's a positive value in the front, it's going to be upright. B now, just to remind us of what B is, we've got y equals -2, x plus 1 squared take 3. So our turning point. Take what's inside the brackets here, make it equal to 0, so I get x equaling -1 and y equaling -3. So I have -1, and I should also have here -3. The dilation factor, the value in front of the bracket is -2. So I take the magnitude of that, so it just means I ignore the sign. So the dilation factor is 2. Notice that with this graph, I have a negative value in front of the bracket. That means that the graph is going to be inverted. So it's going to be this shape. So it's inverted. And of course, to establish what the y-intercept is, I make x equaling 0, so I sub that in to get -5 to produce 0, -5. As I said before, it was inverted. For C, the turning point, I have x minus 5, I make that equal to 0 to get x equaling 5, so the x value is 5, and the y value is 2, so I have 5, 2. The dilation factor, I have think of that as being a -1 out the front. If I look at the magnitude of -1, it's 1, so the dilation factor is just 1. Y-intercept, I sub x equaling 0 into the rule to establish that y is -23, creating a y-intercept of 0, -23. As I said before, it's inverted because of the negative out the front of the bracket. Here, over an 8-hour period, the temperature of the room follows this relationship. So we've got T for temperature and H for hours. It's a quadratic. Express the equation in turning point form and hence sketch the graph of that quadratic relationship. So here I have my T equals H squared minus 6H plus 15. I'm going to get it into turning point form using the completing the square method. So the coefficient of the variable is -6. If I halve that, it's -3, square it 9. So I take my first two terms, H squared minus 6H, and then I add to it that 9, and this will create a perfect square. I haven't lost the 15, so that comes down. And if I'm just randomly adding 9, I need to also subtract 9 to keep everything equal. As expected, these first three terms can be factorized to become H minus 3 squared, so that's just that -3 there. I've got the 15, I've got the -9 still. And that will give us 6. So now I have it in turning point form. I can sketch that easily. I know that my x value or h value is going to be 3. So that should be a 3, guys, not a 2. And that the y value is 6. So that's the position 3, 6. So if you just change that in your notes, so that that's a 3 and that's a 3. Also note that technically it's not an x variable, it's a h variable because I'm using capital T for temperature and h for hours. So that there is a h and we could place a capital T here. I also need to sketch that graph. I know in that turning point form that the dilation factor is +1, so it's going to be upright. And looking at the expanded form, if I substitute h equaling 0 into this, I'm going to get 15. So I know my y-intercept is 15. And so that's all the information I need. B, what is the initial temperature? So the initial temperature is the starting temperature. What is it initially? So I just have to substitute h equaling 0 into the rule. And it wouldn't matter if I put it into the expanded form or the turning point form. but there it is, 0, 15. C, after 2 hours, is the temperature increasing or decreasing? And also after 6 hours, is it decreasing or increasing? So let's take a look at the graph. Remember, this is in fact the position 3, 6. The 2 is just before it. You can see that temperatures are greater here, and they're decreasing all the way until they get to that turning point, 3, 6. So the 2 is to the left of it, so for that, it's decreasing. In part D, we're asked if it's increasing or decreasing at 6 hour mark. So obviously 6 hours takes us to the right-hand side of the turning point, and you can see along here the temperatures are always increasing. And finally, I'm asked, what is the minimum temperature and when does that occur? So the minimum temperature occurs at the minimum turning point, and remember that's the position 3, 6. So the minimum temperature is 6 degrees, and that occurs at the 3 hour mark. Parabolas in expanded form. For the x-intercepts, just make y equal to 0 and solve for x, and that will produce our x-intercepts that we always have to list as a set of pairs. Y-intercept, make x equals 0, sub that in, and again you express it like so. Location of the turning point. We could either convert into turning point form using the completing the square method, or we can use symmetry of the parabola. With the symmetry of the parabola, the turning point occurs halfway between the two x-intercepts. So to find that, then x1 plus x2, where they are the x-intercepts, divided by 2, and that will give you your turning point, and then of course substitute that into the original rule to get the corresponding y value. And we can also use this rule here that will help us get the x value for the turning point. And again, sub that found x value into the original rule to get the corresponding y value. So let's look at sketching some of these. In problem 8, we've got a variety of different rules or equations, and we have to sketch those. So for A, y equals x squared take 4x minus 32. Firstly, consider the shape. In front of the x squared is positive 1, so it's an upright parabola. X-intercept, y equaling 0. I factorise, solve for x, and get x equaling 8 and negative 4. So there's my two intercepts. Y-intercept, make x equaling 0, get negative 32, and I've got 0, negative 32. Where's the turning point occur? I use the completing the square method, and I establish that it's 2, negative 36. So that's all the information I need, and I can draw a graph. Here it is. Looking at B. So B, y equals x squared plus 10x plus 25. Here's my equation. We know it's an upright parabola. I'm able to move that into turning point form really easily because I can recognize that it's already that perfect square. So the turning point occurs at negative 5, 0. The y-intercept, sub x equaling 0 into the rule to get 25, and we know that anyway from the expanded format. Oops. And that's all the information I need, because obviously that's going to be the x-axis as well where it cuts through, so I have that coming. C, y equals negative 2x squared plus 11x minus 15. So for C, which begins over here, y-intercept, firstly, it's going to be an inverted parabola because of that negative out the front. But my y-intercept sub x equaling 0, and I get negative 15. X-intercept, I make y equaling 0. And what I'm going to have to do here, because I can't factorize this expression easily, I'm going to apply the quadratic formula to find out the x-intercepts. So that's my equation. And to find out what x is equal to, I use the quadratic formula and I produce -3 and -5 on 2. So they are my two x-intercepts. The turning point, because it's going to be a bit more difficult for me to convert that into turning point form using the completing the square method, my turning point occurs halfway between those two found x-intercepts. So I established that the turning point occurs at 11 on 4. The y value for that, I just need to sub 11 on 4 into the original, which I do here, to get 1/8. And here's my graph of that. Looking at D now, I had the equation y equals x squared take 49. So for my x-intercept, I just sub in x equaling 0 to get -49. I also know it's going to be upright in appearance because the value in front of the x squared is 1. The x-intercept, I just need to make y equaling 0, so I do that. And I produce positive or -7. And there's my graph. All the information I need. We have a really good modeling question. It's all about a lighthouse. So we have a lighthouse, and we have a function m of x that describes a sandbar around that lighthouse. The m of x tells us how far north we are away from the lighthouse, and the x tells us how far east we are. We have 3 known locations of the sandbar. We have one which is directly north 300 meters, so that's 0, 300. We have one which is 200 west, 200 north, so 200, 200 up. And we have one which is 100 meters east and 200 meters south, so 100 and then 200 down. So notice how I've described that as 100, -200, 0, 300, -200, 200. So that's writing those locations as coordinates. Substitute those points into the original equation to find the equation describing the sandbar. So, obviously there's going to be some kind of parabola sweeping through here, but what are the values of A, B, and C so that we can then work with that function to know exactly where the sandbar is. So I'm going to start off by defining this m of x function. So menu, actions define. I'm going to have m of x equaling a times x squared. You really got to put in that multiplication because otherwise the CAS will just see that as being the variable ax, not an unknown a times the variable x, plus b times x plus c. Hit enter. It's now defined. I'm now going to put in 3 equations based on these points to solve for a, b, and c. So menu, algebra, solve, and I've got 3 equations. Put those in. First equation, I'm going to put m of 100 equals -200. Second equation, I'm going to put m of 0 equals 300. and I'm going to put m of negative 200 equals 200. Now, I'm not solving for x, I'm solving for a, b, and c. And there's my values. So a is negative 11 on 600, b, and c. So I'm now going to work with those solutions and create another function with those in it, which will be m of x, but not with the a, b, and c, with what they actually are. And I'll graph that and work with that for part C. So I'm just going to define another function, so menu actions define. And I'm going to have w of x equals, and I'll bring up the fractional template, negative 11 on 600, oops, times x squared, minus 19 on 6 times x, and then finally plus 300. So that now has been defined. My next move is I'm going to work with a graph. And I'm not going to graph m of x, I'm going to graph that w of x. And of course we're not going to see much because what I've got there, I've got between negative 10 and 10, but negative 6.67 and 6.67. So as you know, if we take a look at this, I've got values going from negative 200 all the way up to 300. So I might go with 500s, I think. So if I go menu, window zoom, window settings, I'm going to go negative 500, 500, negative 500, and 500. And go OK. And now I've got a really strong sense of what the graph looks like. So you can see my lighthouse, the points that I had were there. Relative to the lighthouse, what is the most northerly point of the sandbar? So in other words, what's the y value for this maximum? So there's my lighthouse. The y value here would represent the furthest that the sandbar is away from the lighthouse as far as just considering the northern direction only. Just there. So I need to locate that position, so I'm going to go menu, analyze graphs, and I want the maximum. And what I'll do is I'll sweep from left to right, click on the left hand side of it, sweep across, get to the right, and you can see that the most northerly part of the sandbar occurs at 86.4 meters west, 437 meters north. So what is the most northerly point of the sandbar? It's that position there, which is 437 meters north. Here I have an explanation of everything that I just did and demonstrated. So B, what would you need to show as far as answering this is concerned, is on the left hand side here. So m of x, you state that. You've got your three equations, and then you've got your answers for A, B, and C, and you write it down m of x. That's all you need to show. These are just the CAS steps, that's how you did it. You don't need to demonstrate that. That's just helping you out of how to do it. And for C, the most northerly point is here, and you just show that on your graph. That represents 86.4 meters west, 437 meters north. That's all you need to show. There are your steps of how you achieved it. That's just for your